Swayam Prabha. Digital India. Educated India.
Okay, good morning. So in the previous classes, we were looking at various case studies on life cycle assessment of various plastic products. Just to recap, we were looking at initially about various plastic resins from the cradle to gate analysis, and later on we will look at a lot of products made up of plastics, paper, and their comparison. We were looking at disposable food containers, clamshells. Then we were looking at plastic bags, cotton bags, paper bags, and then relative comparison of impacts. And so in that sequence, now we look at plastic bottles and cups, and what is the LCA outcome of these. So in this talk, I will be talking about two literature. One is looking at a PLA based and petroleum based plastic bottles. So PLA, as you know, is a bioplastic. It is actually derived from corn. We looked at LCA of PLA resin already, whereas petroleum based would be looking at PET or other kinds of bottles. Then the second one is a research article came in Science in 1991, which kind of did a very detailed analysis between paper cup versus polystyrene foam based cups. Okay, so as of today, you see a lot of paper cups being used in the coffee and tea beverage stalls. So that I thought it's relevant to discuss both bottles and cups in this particular lecture. Okay, so the first one talks about bottles. So here, we are talking about LCA, we are talking about forming assumptions, looking at inventory, and then doing the impact analysis, and then interpret it. Okay, those are the 4 steps. The first step is to kind of look at the context in which we want to do this LCA. So in this study, they are looking at 10,000 water bottles with a capacity of 12 ounces. 12 ounces means something roughly about 360 ml. Okay, 1 ounce is roughly about 30 ml. So in this LC analysis, a bottle comes with the main bottle. It also comes with the lid, a cap. Okay, and then it also comes with the wrapper or a label that will have information about the brand, various packaging details, etc., etc. So in this analysis, they have basically ignored both cap and labels. So if you want to include both caps and label, they are typically made up of different kind of materials. Okay, even in PET bottles, the cap is used typically from HDPE and the label is used from polypropylene. Okay, so but here I think they are keeping that out of the context in this example. And then they are talking about PLA and PET, and they also identify that the heating value is little different between PLA and PET. That is to do with the chemical or thermal nature of the material. We saw DSC, we saw several thermal properties of plastics, and that is related to the molecular structure, arrangement, and all that. Now if you look at the weight of the bottle that is used to carry same amount of volume, because the thickness could be different, because the material strengths are different, you see PLA bottle takes about 21.0 grams and PET is 20.3. So actually they are roughly the same in terms of mass. Okay. So data is actually obtained from based on the US life cycle inventory database. This is a government repository that gives all this data, and this particular entire analysis is taken from this paper. If you remember, we actually talked about this particular paper in one of the previous class where we compared between different resins. Okay, so the data from that report comes as an input to this analysis. Okay, so you don't have to do again from the resin. Resin calculations are already done. You just import it. Okay, rather than going back to corn, water conversion. Okay, so that means sometimes the LC analysis can be done not necessarily from a scratch, but it can be built on existing framework like this one. So in terms of end of life options, for PLA, even though it is can be composted, so here the option is to keep it non-compostable. Okay, so composting is not an option in this particular study. In the case of cradle to grave analysis, 80% goes to landfilling, 20% goes to waste to energy, and PET may be recycled at a rate of about 23.5%. Okay, how do we say this? How do we make these kind of assumptions? Based on the region where these bottles are used and what sort of recycling options exist, which is typically supported by the government agencies or other NGOs. Okay, so you have to look at what is reality, okay, or whether the producer itself is going to collect it and use this. So you have to see that the end of life options are quite variable because the region, the government, the citizens, the society, how they want to handle this. Okay, so it's quite variable. So we have to be very careful about the conclusion is tied up with this end of life options. Whereas the environmental effects in terms of pollution, air pollution, water pollution, and acidification, eutrophication, all that is actually considered. Transportation was included for the movement of plastic resins from plastic producers to bottle converters. Okay, and PLA had about, you can see that it's based on truck transportation, and for PET so many miles, for PLA so many miles. This is because again, maybe this is done in a US kind of system, and there are people who actually produce PLA resins whose numbers could be far less compared to number of PET producers. So if you want to bring these resins from the manufacturers, the transportation can have quite a lot of impact. The one that is more readily available or accessible would have lesser transportation costs compared to something that is not readily available. Okay, so you can see the difference between the miles of transportation required for the PLA versus PET. PLA only few companies produce, PET a lot of companies produce in the US. So in about 96 miles you can get PET, whereas to resource PLA an average of about 425 miles, thousands of miles you probably have to work with. Few other data, as you can see that the eutrophication and acidification data were actually obtained from one of the previous clamshell study I presented in the previous class. So you can see that not everything is from scratch. A lot of data from resin data, from the pollution, eutrophication, acidification data of previously formed products can also be used. Okay, so here is the summary. So what we are looking at here, we are looking at PLA bottles. There is also another PLA bottle here. The difference between these two is that in the first column, the PLA related data, inventory data, correspond to a timeline of 2005. Okay, a lot of process optimization happened, a lot of energy consumption reduced, so a lot of modification happened, and that led to a new set of data. I think this is about 2010 or 11, I think. Okay, you got a new set of data. So you can see there is a difference between the first column and the last column in all the quantities. Okay, broadly you can see that there is some sort of an improvement from 2005 data to 2010 data. Why? If you look at the energy consumption, the previously produced PLA process consumes about 19,000 megajoules, whereas the newer version of PLA has about 16,560. So there is some saving of energy of the new material. Similarly, if you look at carbon dioxide emission, there is a reduction, which is a good thing. And if you look at solid waste generated, that doesn't change. And water eutrophication, there is some drop, and acidification also there is some drop. So maybe we should be looking at this data, provided that you got a new batch of PLA for making your bottle. If you are still having an inventory of PLA resins made in 2005 data, then you should be looking at this data. So that's the way to look at it. Then we have virgin PET. Virgin PET, there is no timeline because PET production is pretty much standardized, and wherever you get it from, whichever year you get it, they are pretty much the same. Okay, there's not much of an optimization going on like PLA is going on. So you can see that maybe if you compare between these, so you should be comparing between this, let's say. Okay, energy consumption not much different, but clearly the CO2 emission is little higher for PET. I think solid waste is comparable. The eutrophication of water and acidification are quite less for PET compared to your PLA. And then there's one more column here, column 3, which has instead of using virgin PET based bottle, you could probably have 25% post consumer recycled PET along with 70% of virgin. So therefore you recycle some fraction, and there you can see that you have a quite kind of comparable situation with this data. You can see energy consumption is less, global warming is not so bad, and solid waste is less, eutrophication is less, and acidification also less. So what it means is, if it is possible to actually collect PET bottles, recycle 25%, put it back into the PET bottle production, you can actually balance out between the PLA and rPET. Okay, so and we know that now PET is quite a bit recycled. From an Indian context, the recycled PETs are typically used for polyester garment making, but in advanced countries, rPET actually goes back into bottle productions. For example, the Coca-Cola actually comes with the rPET recycled bottles in Europe. Okay, you can see the color difference. The virgin plastic would look very transparent like this, but the recycled one will have a small kind of a light yellowish orange tinge that you can see. Okay, that kind of tells you it's a recycled or there is some fraction of recycled plastic. So through this kind of LCA analysis, you can say that the option of going completely BLA versus recycled PET, they both have a similar kind of impact. Whatever data we presented in the previous is being basically replotted with some sort of a normalization. So we take all the data of this PLA new version as unit of 1 with respect to that you scale and look at the ratios of energy and everything, and as the conclusion remain the same, you can see that this is your standard case PLA. This is probably the one that we should be looking at, and you can see these numbers are actually just below 1 or 1 out. Only this case I think it has more than 1, otherwise it's less than 1. When you say less than 1, it means in those factors the recycled PET outweighs the PLA, virgin PLA, right? And so similarly, if you look at PET, virgin PET, these numbers are a little higher than 1 in few cases. Okay, so basically the conclusion of this study is the following, that the PLA resin based bottles and recycled, at least 25% recycled PET bottles, they have almost equivalent environmental impacts. Okay. All right. So now I want to go to this second case, which kind of compares between paper cup and polystyrene foam based cup. Okay. In the market right now, you don't see much polystyrene foam cups. I think it is gone away with. Okay, but you see a lot of paper cups, right, in hostels, in the cafeteria and malls and everywhere. For coffee, cold beverages like juices, hot beverages like coffee, tea is usually now served in plastic cups. So this study tries to look at is it really the fact that papers are better, environmentally better than foam based cups or not. Okay, so here some introductory materials given. So if you think about paper and polyfoam, we are looking at what are the raw material and what are the other chemicals you may be using in the process of making those material or the products. Okay, so if you consider paper, we know that the raw material is wood, right, and wood is renewable. Okay, you can grow plants, there's a lead time for getting a tree grown, cut and then regrown, all that. Okay, but it's renewable as long as you have water, land and etc. So when you look at wood, the problem with that wood is that you have to cut it somewhere from, okay, and that means you have to have access to reach that place where wood is present. So road transportation, laying roads, construction have to be also factored in, okay. And you're also then thinking about deforestation, and then you're talking about watershed changes. So the presence of trees and forest controls how water flows from one place to the other place. When you actually kind of disturb that ecosystem, you have more proneness in drought and flood situation, okay. It's a very complex process by which trees play a bigger role in controlling water flow or watershed, okay. So those are also something that we have to keep in mind. And then in terms of, even though wood is renewable, but you don't get paper just from there, okay. You have to do a lot of processing. Pulping process requires a lot of chemicals, okay. Sodium hydroxide, sulfuric acid, calcium hydroxide. So you can see a lot of inorganic chemicals and acids are used at quite some concentration to actually get the cellulose out of wood, okay, for paper making. So that also have to be taken into account. Then paper cups are coated with typically adhesives and wax. You can see if you touch the inner side of the paper, you will see some sort of a very shiny or smooth coating is present. That's what keep the liquid, hot liquid or water from seeping from that, okay. Whereas outer surface, if you touch, you will see some sort of a roughness which feels like paper, okay. So outer surface is paper, but the inner definitely will have a particular thickness of wax or a plastic or something, okay. And the problem with this is, the moment you actually throw it, the paper industry cannot recycle that because of the wax and the adhesive or the plastic that is in the inner layer, okay. So only end option seems to be you incinerate it, right, or just landfill it, okay. Recycling or recovering the fiber from there, paper industry is not willing to do, okay. Now if you come to this polyfoam, when we say polyfoam, we are talking about expanded polystyrene, okay. What's the raw material for styrene? I don't know, did we do polystyrene resin LCA? Maybe not. So polystyrene basically has to be synthesized from benzene, okay. You do an alkalization of benzene, you get styrene, and then you polymerize it, you get polystyrene, okay. So the raw material in this case is basically coming from oil and gas, which is non-renewable. Now again, where do you get oil and gas? Again, you have to do exploration. Mostly it's obtained from sea or land, okay. There's a drilling required. There's again clearance of land, transportation, and when you also drill, you also spill. When you spill, nothing can grow in the spilled site, okay. You're basically then affecting grazing opportunity for animals or plant growth, okay. Again, you're creating a kind of environmental impact by drilling oil. Transportation of oil across sea, and if spillage happens and how it affects marine life is a whole lot of another story. Algal bloom, marine snow formation is a whole lot of thing that we have to worry about. So clearly we know that plants and animals in the land, in the ocean are affected by accidental spillages of oil and gas. Now if you think about from the oil and gas to the polystyrene, you typically do, like I said, alkylation of benzene. This requires some sort of catalyst. You need aluminum chloride, some amount of acids and bases to use it. And then since it's an expanded, you need something called a blowing agent, okay, that will create bubbles, that will create gas on which this polymerization will happen. So you get a foamy structure. So pentane is used as one of the blowing agent. Before that, some chlorofluorocarbons were used, but now that is banned, okay. So then you're talking about again pentane, which is again coming from oil and gas industry. Now if you think about end of life option for polystyrene, you can actually recycle it, and you cannot put it back into food product, because if you want to use it for food application, it has to be a virgin plastic, it cannot be recycled plastic. There are restrictions on standard based, some standards have to be met for food application. So that means if you're going to have a coffee polystyrene cup, you can recycle, but you cannot make another cup for coffee, or you cannot make another cup for water or juice, but it can go for other application. What are the other applications? Well, you can use it for packaging, insulation, flotation systems, or maybe furnitures, and so on. So, okay. So, there are a lot of options for polystyrene as long as you are able to recycle it. Okay. It may not go back to the original application, but there are other applications one can think of. Okay. So, I am kind of laying out the context, what are the things that are necessary for making this material, what are the other chemicals used in making these products, and what are the end of life options. Okay. So, with all this consideration, this paper talks about some comparative statements. So, here per cup basis, how much raw material is used, right. So, here in the raw material, for the case of paper, you need wood to the tune of some 33 grams for 1 cup, and petroleum fractions about 4.1 grams, other chemicals like I said, lot of inorganic chemicals about 1.8. The finished final cup will weigh about 10.1 grams. Okay. Whereas if you come to this polystyrene foam, yeah, wood is not required, of course, it's not a renewable material, but it does take care of it does come from this oil and gas. So, you use about 3.2 grams of oil and gas, other chemicals like I said, aluminum chloride, acids and bases and all that. But if you think about the weight of this plastic foam, it's about 1.5 grams only, because it is a very low density. So, you can create the cup with a very small amount of volume. The same comparison we did, if you remember, in the case of clamshells, the disposable container clamshells, when we try to compare between foam, PS foam versus let us say PET or paper, right. So, this difference we saw already. And then there is some sort of a cost estimate that says that if polystyrene foam based cup is rupees X, it is going to be about 250% more for the paper cup. Okay. That is because of all the energy cost and material cost that is involved. So, that means by moving to a paper cup, you are paying more, you are basically making the customer pay more. Okay. So, that is one. So, here we are looking at various comparisons. One thing you will note is that the way that this comparison is made is a little different from the other tables I have shown before, because those tables I have shown are based on some LCA softwares, Cyma Pro, Gabi and other things, but this is an older study, okay, maybe before this actual softwares came. So, this was probably done by hand or by other local codes or something. So, you can see that they are trying to compare between paper cup and polyfoam. So, now they are categorized into utilities, water, steam, energy, etc., and then effluents, that is water waste, and then emissions to air. Okay. I mean, if you just without looking at details, if you just compare two columns, you can clearly see that a lot of zeros for the poly foam and there are quite a lot of numbers on the paper cup. Okay. So, let us see one by one. So, what happens when you look at steam, okay, as an utility? The steam in kilograms, you need anywhere between 9,000 to 12,000 kilogram of steam per metric ton of the paper material. Okay. The previous table we compared between per piece of paper cup versus polystyrene cup. When we try to compare this waste generator and utility, we try to compare for 1 metric ton of material, what are the comparisons. What that means is, if you look at back in the previous table, we have about the ratio of 1.5 to 10, right. So, that means for equal mass, you can actually make 6 cups more in the case of polystyrene versus paper, right, because of the weight ratio is 1.5 to 10.1. So, that means even though here we compare between kilogram basis or tons basis, this is not based on the number. If you want to compare with the number, the polyfoam cups could be made 6 times more in number than in plastic, okay, but that is okay. But in any way, we are here, this is based on the per metric ton of the material, not per ton of cups. Okay. Okay. So, even then you see that the steam utility is half or 50% less in the case of polyfoam. And if you look at the power required, again we see a larger difference, 4 to 5 times. Cooling water requirement, polyfoam requires 3 times more than paper cup. And in terms of effluent, this is given in terms of meter cube, that means thousands of liters. So paper cup requires a lot of, it produces a lot of waste effluent compared to polyfoam. And within that, if you compare suspended solid, biological oxygen demand, and chlorines and metal salts, because in the pulping process you have all these additional chemicals that are there, and that's going to reflect in your effluent stream. Okay, and whereas those chemicals or any other chemical, the amount of chemicals, inorganic chemical used in polystyrene is much less, because mostly a thermal based thing. You don't involve water, you don't involve very much of the salts. So clearly that amount of water waste created or the contamination in the water is much less in the case of polyfoam. And then if you think about air emission, again then we are talking about chlorine, chlorine dioxide, sulfides, particulates, a lot of things, pentane, etc., etc. So you can see that the pentane is the one that gives a lot of emission because of the blowing agent, and similarly sulfur dioxide also is comparable, but all the other ones, the chlorine emission and others, are quite less. Okay. Then they are also comparing this end of life options, what are possible. So if you see after use, okay, once the cup is used, if you have a paper cup, as I said before, the adhesives of wax that is present in the inner wall puts a lot of constraint on recyclability of paper cups. Okay. Whereas in the case of polyfoam, polystyrene foam, the recycling options are high, because like I said, you can extrude back into some sort of a resin, and that can be used for various applications like I mentioned, right? Insulation, packaging, floating operations, and furniture, and etc. And then they are talking about ultimate disposal, how much heat you can recover, how much landfill, and how much is biodegradable. So here if you see, paper of course biodegrades, okay, if you throw in the thing, but this is not the adhesive layer, just only the paper fiber. Okay, whereas in the polystyrene, if you throw it, if you're going to litter it, if you're going to landfill it, it's going to remain inert. And then we have other issues of microplastic, nanoplastic formation over a long period of time, and how it can leach from water, through water into various bodies. Okay, so those are some of the other considerations. So finally, this author concludes very nicely that he's saying that whether it is a paper cup or polystyrene cup, if you can make it as a multi-use rather than a single use, then you have a lesser impact than single use corresponding paper cup. That means if you have a paper cup, if you can use it, reuse it over and over, multiple use, and that would have much lesser impact than making new paper cups every time for a single use. Okay, and the same thing holds for the polystyrene cup also. That's one. The second conclusion is a little bit kind of counterintuitive. He says that for single use applications, okay, if you're going to use only single use, it would appear that polystyrene foam cups should be given a much more even-handed assessment as regards their environmental impact relative to paper cups than they have received during the last few years. When the time of this paper came, at the time the transition was happening already in the US from plastic cups to paper cups, because it's a common intuition that paper are biodegradable, so let's move to paper. Okay, but this paper kind of justifies, if you really look at the details of what goes into making of a paper cup, how much waste created, how much energy required, and how much environmental damage that causes. He's saying that it is not that superior compared to polyfoams. Okay, so he's appealing to policy makers to give a due consideration to polyfoams, and what they say is that as long as you are having enough recycling possibilities for polystyrene, then it's a good deal. Okay, so that's the context that they are talking about. It's a very enjoyable read. You should refer to this paper. Okay, this is a very short paper, so 2-page paper, and after that he published a more extensive article in a lot of details, and so if you're really interested, you should look at this. Yesterday I visited a big recycling unit in Bangalore, I wish to take you all there, but because of logistic issues and other things, I could not. So the next best thing is I visited them. So basically, what they do is it's a company. They go to different outlets and collect the wastes. Okay, example could be they go to, let's say, Decathlon. So in Decathlon they sell a lot of products, and then they create a lot of packaging waste. They just collect it. And they go to some clothing stores like Zudio or Westside or Lifestyle. Okay, again they whatever waste they create, they just buy it or they collect it. Many times the shop owners pay the transportation charges to come and collect the packages. Some other people sell the waste to this waste collector, okay, depending upon the value and competition. If the same waste is requested by many recyclers, then the shopkeeper would try to put a price and try to maximize his profit. Okay, very logical. Whereas there are other waste which nobody wants it and he has to dispose it off. Sometimes the shopkeeper will will actually pay to for someone to come and collect it. Okay, so they will have variety of such situations. Okay, there are shopkeepers who will give it for free. There are other people who will pay for the transportation charges. There are other people who will pay you to take the garbage and also for the transportation. They have variety of things. So what are the things they collect? They collect pretty much everything. Cardboard boxes, food beverage cans, single-use plastic covers, the straps that comes on carton boxes, right, and the plastic waste bins. Okay, so many things they collect. Okay, and then they have and then what the way they do the things is, they do not go to municipal waste. They do not go to waste that is contaminated with food or with other things. Okay, so they try to collect the waste as pure as possible. Okay, the purest one I was told was when Zudio actually collects inventory from other textile manufacturers, they come in a cover. Okay, there is a plastic cover, so they take it and then display it, and now the cover is a waste, but that cover is not contaminated yet, so they actually safely put it in some place and that is collected. So because that is a purest form, they don't have to wash it, they don't have to clean it, so that is in a near pure form. Okay, so they always try to get that kind of a waste. So now what do they do with it? So they have several mechanisms. Okay, so they first categorize. Okay, the one they have the largest volume is the carton boxes. Okay, so they have a big machine that basically compresses into bales. Okay, and that is sent to a paper industry, and paper industry collects them as a raw material. They make craft paper out of that, and they sell the same craft paper to the same recycler. Recycler takes that the finished paper, and this paper is given to somebody who makes a paper bag, and this paper bag goes to the place where he collected the waste in the first place. Okay, so they say we are doing a circular economy. We collect the waste from you, right, and then I do something, I give it to somebody to do a value addition. I take that value added product, make another product, and I sell it back to you. So in this case, he may be collecting plastics, but maybe he is selling you a paper bag. So it is not the transaction is always paper to paper. It can go from I collect paper from you, but I may give you plastic, or I may collect plastic from you, I may give you paper. So that is about the life cycle of the carton boxes. Okay, very highly recycled product. Then they have this let's say polyethylene, low density polyethylene wastes. So they have an extruder facility and they have a mechanical grinding machines. So they put this through and get into small scraps, and then they put it into an extruder. They extrude it, they pelletize it, and they get actually a LDPE resin. And this LDPE resin are actually taken by people who actually make LDPE bags. So they, instead of buying virgin resin, they take this recycled resin, put it in their own production process, and they make plastic resin. So this waste collector collects the LDPE bags, regranulate it, sell it as a recycled product. and then this goes again back into the plastic bag. So they complete that cycle. Now when we asked what is the real problem for you, he said the real problems are the biodegradable plastics. He says he gets a lot of waste that comes with this notion, this is not a plastic, this is a biodegradable, biocompostable, all kinds of certification. So they initially thought if it is if it is compostable, they have a composting unit also. So they put some composting thing, and they show that many of these bags are actually not compostable. And what they actually get is, because of low density, they basically start floating on the surface of water in that in the composting unit, and it creates a lot of slurry, and it is not manageable. So it kind of disrupts the entire process of other composting wastes. Okay, so they have not been able to do composting. The next option is they were trying to regranulate it and then try to recycle it, but that also what they see is that the recycled biopolymer cannot be blown into a film like the virgin one. So, and the only option for them is to then incinerate it. Where do they do incineration? They send it to a cement industry. Okay, cement industry collect these plastic waste, whichever is not recyclable or reusable. They mix it with coal and burn it off. Okay, I think they have some permission to use up to 5% or 10% of plastic along with their coal. So their idea is to minimize the incineration, because if you incinerate, again you are polluting it. The best case for them would be like how it was managed in the case of the cotton boxes, where you have a pretty much near complete recycling. Okay, so the bioplastic, as we see in the in the market, as a consumer we are convinced, yeah, it's bioplastic, so I'm not feeling guilty about it, so we buy. But then if you think about, if you ask, the real answer should come from a recycler, whether he is able to actually recycle it. Okay, the people whom we visited, these are really serious people about circularity and sustainability, and they said that the recycling is a big issue. The second thing they said is that they also collect this paper cups, like I was saying here. They also said the same thing. The paper cups comes with the inner layer, and that paper industry do not accept because they are not able to remove that. Okay, so that is also some unsolved problem for them. Again, they have to send it to incineration or landfill. Okay, then Jackie is another brand. They also showed that they use some paper that is also coated with some sort of an adhesive, and that also has the same issue. And they say that if you can effectively remove this adhesive, what is left behind is a white paper, and white paper is a more value added product than a craft paper. So they were suggesting you take a bio cup or this kind of paper with adhesive. If you can come up with a method to remove this adhesive and keep only the white fiber, it has a very high value. So based on all this, I am trying to put up some project proposals. Okay, I want you to take a look at it and then start working on one of those projects. Okay, so that you can also play a role in this bioplastic recycling options, right? So that's all I have today. I'll see you in next class.